We were looking at the centrifugal pump actually. Maybe in the last class we looked at the different parameters for the centrifugal pump. One such parameter is the what we call it as a maximum suction lift. So what is it actually? It's so critical that where I should see what is the maximum possible your center line, or we can call it as the eye of the impeller. What should be its height from the sump level? What are the maximum thing? So considering your atmospheric head. So your atmosphere, if you look, I think from the Bernoulli's equation we got this expression. So maximum suction lift actually is equal to HA minus of all the things. Now the same expression whatever I have, no, this expression I can write it as MSL is equal to your atmospheric head minus, so everything I'm going to bring under one bracket plus HFS, same thing. Now if you observe closely, see, ideally speaking, HA should be my maximum suction lift. That means your pump has to work under atmospheric head. As this is very difficult for us, so practically there should be something which is directed. So that is your vapor head or the head at your maybe your eye of the impeller. There is a little bit of kinetic energy and the frictional losses in your suction point. Now, to be very specific, this should be as much as possible minimum. It can't be zero, but this should be minimum. Now, so there are certain things which need to be taken care. That is factors that affect this maximum suction. Let's look into that certain factors. Okay, factors affecting maximum suction lift. Okay. Now, say for example, you have your HA. I told that is atmospheric height. Now, suppose if I install this pump at different altitude. So, one such factor which is very critical on your maximum suction lift is the altitude. We call it as height at which the centrifugal pump has to be installed. Okay, the height at which your centrifugal pump has to be installed. Where I am supposed to keep this centrifugal pump. So this has a very impact on your HA. See, with an increase in HA, with an increase in altitude, your atmospheric head will go down. Say for example, I install the centrifugal pump in Bangalore, and if I try to install the same centrifugal pump on some hill station, so its behavior is completely different. This is the first parameter. Second parameter. See, if I use a smooth plastic PVC pipe, or if I use some kind of a metal pipe, its properties are different. So the pipe parameters has a major impact on your suction, that is your friction on the suction, that is HFS. What are those actually? It is your friction, even the length of the pipe, okay, the diameter of the pipe, and there are some pipe fittings we put actually, maybe at the end I can put a valve, or I can put a bend, or I can put a 180-degree bend, lot many things we put. So those are called as fittings. So your friction, that is the friction, inside frictional. So if it is a smooth pipe or whatever it may be, so those things, the length of the pipe, higher the length of the pipe, your friction factor will increase. And also the fluid velocity, the eye of the impeller. The fluid velocity at the eye of the impeller. At the eye of the impeller. Okay, this should be minimum. See, this should be, we call it as V2, that is 2 is the maybe 2 is the point at which your eye is, impeller eye is there. This should be minimum. If this is minimum, then the V square, V2 square by 2G will be small. But it can't be 0. But it should be minimum. And also your ambient conditions. See, your ambient or atmospheric temperatures. Your ambient, or we call it as atmospheric temperature, it has a major impact on your vapor height. Okay, if my temperature is high, what will happen to your HV? HV also will increase. That means your vapor, so your vapor head also will increase. So what should we have? We should have a decent or lower temperature. I should be able to maintain my atmospheric, or the pump should be installed in such a way that roughly around 25 degrees or 30 degrees. So the temperature will have a major impact on vaporization of your fluid, what you are handling. Okay, these are some of the important factors, water type. So one is altitude, your parameters of your pipe, the fluid velocity at the eye of the impeller, and your temperature. So these 4 things are very, very important on choosing your maximum suction lift. Okay, once we know the maximum suction lift, we have one more parameter that is called as net positive suction head. Okay, net positive suction head. Suction head. On some of the books they call this as NPSH. Now when you look at the NPSH, there are 2 things. Okay, NPSH provided from the manufacturers. Provided from the manufacturer. Okay, or you can call that as required. You can't go below that. Okay, then NPSH, that is available at the maybe installation point, at the location or installation point. See, 2 things are very, very important. Okay, now to be very practical, this NPSH available, we call it as NPSH available should be slightly greater than NPSH required, or it can be greater than that. So you will tell that this is the what NPSH you have to maintain. Fine. Then NPSH available will be always greater than your. Well, we'll look into that. What is actually? I will try to put a simple sketch and try to make you understand what is it NPSH. Say I am trying to install a pump. So I do have a sump. Okay, this is my sump. Sump, it has some water level. So this is your free surface. We call it as free surface. Okay, there is an atmospheric head. We call it as atmospheric head. Okay, if I try to put the head on my this particular thing, so let me show you. This is my head. I'll try to show it as a vertical thing. Okay, this is your head. Under this, so the maximum possible is my your atmospheric head actually. So that is I call it as HA. This is my HA. This is an ideally speaking your maximum suction lift. Now there are certain amount of friction and all those things. Your vapor head, all those things and all. They will take away little bit of your this thing. So HA. So your pump can be installed at this particular point. Let me call this as a particular point. Okay, then so this is your HV plus V2 square by 2G plus HFS. Then what is it actually? That is your maximum suction lift. So this is your the losses. So this becomes your maximum suction lift. This becomes your maximum suction lift. That means I should be able to have my pump installed at this particular height. Okay, this is so I can call this as upper limit. Okay, now there is something called as your suction head. See, this is what I need. MSL is what is I required. But there is something called your suction head. Every time I can't keep my pump at the MSL level, I will be keeping it at a lower level. Suppose I try to install my pump at a slightly lower level like this. Okay, this is where I want to put my pump. So this is the pump where you are supposed to install theoretically, but I am trying to install my pump at this particular point. So this becomes my this becomes my lower limit, and this is my suction head. That is my suction head. Okay, now what is this actually? This is your NPSH available. So NPSH available. See, NPSH required means you will tell that this HS should be maximum. So NPSH available is greater than NPSH required. So installation, see, I have upper limit, I have a lower limit. Okay, this is the NPSH available, it's a difference. So NPSH required and NPSH available are little slightly different. So if you look into this particular equation, what is your NPSH? I can call it as NPSH is equal to difference between your maximum suction lift and your suction head. Or what is your MSL? This is HA minus HV minus V2 square by 2G minus your HFS minus HS, or I can write it as your NPSH. This is the available, actually this is HA minus HV plus V2 square by 2G plus HFS plus HS. So this is your what we call it as NPSH available at any given point. Okay, this is available at the installation point, at installation point. So like this, is it necessary? See, this is HSE. I am going for this particular thing. So like this, I can go for, see, I can install my pump anywhere in between this, anywhere between this particular two divisions, between your upper specific limit and lower specific limit, I can install my pump. So you are required, see, NPSH available and NPSH required. You have to be very careful with it. So NPSH required means I should be able to have that number. So that at any given point I should be able to maintain that. So what is this NPSH available? Suppose this is 2 meters. So what is your NPSH required? You will tell that 1.4 meters. That means I can see required, you will tell that, see, available, see, your NPSH required maybe in between, see, NPSH required maybe somewhere in between this particular 2 points, between your upper specific and lower specific, which a manufacturer will tell that yes, you have to install this particular point. And your pump, maybe your somewhere your plumber or someone, you will try to calculate and you will tell that yes, I'm going to install at this particular point and this should be my number. And if I try to maintain that number, your pump will start maybe delivering the fluid. So at any given point, I should ensure that this NPSH is maintained. Okay, maximum suction lift and your net positive suction net is very, very important when you are dealing with your centrifugal pump. You got it? Okay. Once you know about this particular thing, there is one more point which is very important. So that is minimum starting speed of a centrifugal pump. Okay. Minimum starting speed of a centrifugal pump. What is it actually? See, the pump has to rotate at a particular speed to develop a head. Okay, it is the speed. It is the speed. It is a speed. It's a minimum speed actually. Let me call it as it is the minimum speed required for the pump to deliver the fluid. It has to run at a particular RPM, then only fluid will start rotating. Say for example, I have an impeller like this. See, this is your casing and this is an impeller. Okay, I have an impeller like this. Okay, your impeller may be having something like this. I have a 5 impeller like this. Now fluid has to come out like this. The fluid has to come out. This is rotating and fluid has to come out like this. So it has to rotate at a particular speed. So now if you closely observe, when the fluid is coming out, I do have what is called as a delivery valve here. So this is your delivery valve. See, this pump can operate at 2 different conditions. One is either my delivery valve is closed or delivery valve is open. See, if the delivery valve is open, then the fluid can come out. If the delivery valve is closed, then the fluid will not come out. Okay. Now, when the delivery valve is open, when the fluid starts coming out, what is the particular speed? What is that particular speed? Is the rated speed is different. See, rated speed is different from, in most of the pump, we have the rated speed. So 3000 RPM, 3600 RPM or 7500 RPM. That is a rated speed. That depends on your motor or whatever it may be, coupling, all those things. But minimum speed is required so that at which the pump will start delivering the, that means pump will start delivering the fluid into a delivery pipe. It is the speed the impeller has to rotate to start delivering the fluid. That means to start, let me call it as to start delivering the fluid. Let me call this as pump required to start delivering the fluid. We call it as delivering the fluid. That is the minimum speed required so that the pump will start delivering the fluid. So to get an expression for it, okay, expression for this minimum speed, how can I do that actually? To get that expression for this particular thing, we will consider the manometric head. So the manometric, what is manometric head? Manometric is the head under which your pump is working. So manometric head is given in terms of velocities. Okay. So now what is it actually? It is actually, if you look into the equation, W by M into G, or we call that as HM, manometric head, is equal to your kinetic V2 square minus V1 square by 2G plus U2 square minus U1 square by 2G plus VR1 square minus VR2 square by 2G. Okay. Now here, see, I'm see, I'm looking at what is happening in the impeller. So this is my impeller. How much of it is only from the impeller? I'm not looking at what is the velocity with which the fluid enters. That is, I'm not looking at this particular thing. What is the relative velocity? I'm not looking at it. I'm looking at only the quantity which is mainly developed due to the centrifugal. Okay. Now, to see, this is the required. See, the required head is actually, so there is a little bit of order. See, if you want to closely observe here, actually, there is a little bit of forced vortex induced. The forced vortex is induced to develop the head. Now, this is your manometric head. Okay. So, impeller, see, when the manometric is developed, so what is the minimum requirement for the manometric head to develop? The impeller has to be filled with water. Okay. Now, whenever, see, if suppose HM is the manometric head, if suppose HP is the pump required, that head required by the pump, it should be greater than your manometric head or greater than or equal to this. Then only, see, under these conditions, pump starts delivering fluid. It should be equal to that or greater than that. Okay. Now, if you closely look into this, actually, that is your HP should be greater than your U2 square minus U1 square by 2G. That means your pump, see, whatever this particular thing head, actually, the pump required, the HP is the, let me call this as HP is the head required by the pump to deliver fluid. This is required. What is U1 and U2? U1 is equal to your peripheral velocity, pi d n by 60. So, pi d1 n by 60. So, your U2 is pi d2 n by 60. Okay. So, I can write it as, so as U1 is equal to pi d1 n by 60 and your U2 is equal to pi d2 n by 60. So, let me substitute for this in the equation. So, your HP will be greater than or equal to, so U2 square I can write it as pi square d2 square n square minus pi square d1 square into n square by 60 square. Okay, by 60 square divided by 2G. Okay, I can write it as whole thing divided by 60 square into 2G. So now, what is required actually? See, I am looking at this value of this n. See, n is the speed with which the pump has to develop. Now, for n is equal to n minimum, that is minimum speed required. Minimum speed required. Minimum speed required. So what I will do is I will try to substitute this in terms of n minimum. So I will call it as HP is equal to greater than or equal to your pi square d2 square n minimum square minus pi square d1 square n minimum square divided by 60 square into 2 into G. So now I'll do a little bit of cross multiplication. I want n minimum square. So n minimum square is equal to greater than or equal to, so I'll do this particular thing, 60 square into 60 square into 60 square by pi square into d2 square minus d1 square. Okay. Then 60 square into 2G into Hn. 2G into Hn. Okay. So this should be my minimum starting speed. So this should be my minimum starting speed. See, this particular thing, so this should be greater than this. This should be greater than your HM. Okay. So now, so this particular thing, say I'm trying to put your pump. See, this is this particular thing. This should be greater than or equal to your pump speed. So that's why I'm trying to consider this HM here. See, this side I can put HM. Okay, that means I'm trying to compare or consider with respect to your manometric head, or I can write N minimum is equal to greater than or equal to square root of 60 square into 2G into HM divided by pi square into D2 square minus D1 square. So if I call this as expression number 1, so this I can call it as expression number 2. So now if you look closely observe 2, I can get the minimum starting speed using this formula. 60 square into 2G HM or manometric head divided by pi square into D2 square minus D1 square, where D2 is the diameter and D1 is the half diameter. This is for a centrifugal pump. So sometimes I may have to replace this manometric head your Euler head. So for that actually, so you have the manometric efficiency given by, it's equal to your manometric head by your Euler head, or I can write your manometric head is equal to your manometric efficiency into Euler head, or I can write N minimum is equal greater than or equal to square root of 60 square into 2 into G into manometric efficiency into HE divided by pi square into D2 square minus D1 square. Let me call this as expression number 3. So this is the minimum starting speed expression for in terms of manometric head, in terms of Euler head. So the pump has to run at this particular speed to start delivering the fluid. Otherwise, what will happen if the pump doesn't run at this particular speed? Say, suppose if I try to get this number, if I substitute all the things for a given condition, so I am going to get it as 120 RPM. The rated speed is 3000 RPM. Leave it. Rated speed is different. So if I get 120 RPM as the minimum starting speed, if the pump is rotating at 100 RPM, it won't deliver the fluid. So the moment pump starts reaching 120 RPM or slightly greater than 120 RPM or greater than 120 RPM, maybe 300 RPM or 400 RPM number, which is greater than 120 RPM, the pump will start delivering the fluid. So as this number keeps increasing towards its rated RPM, the pump will start delivering more and more fluid. That is, the quantity of the discharge from the fluid will start. But pump has to run at this minimum speed. And what is the expression for it? How can I get it actually? This is how you can get it. So based on your manometric head or based on your Euler head, I can get this expression. Now there are two more things before we go into multi-staging actually. The two things which we always come across. One is the priming. So priming in pumps actually. Nowadays, I think because of the advance in technology, most of the centrifugal pumps now we come across, they're all self-running pumps. Okay. But what is this particular thing? See, I do have an impeller. See, suppose I have an impeller like this. So this is your casing and this is your impeller. Okay, I have an impeller like this. So I have to ensure that this impeller is filled with water. Before starting, I have to ensure that it is filled with water. If I don't fill this particular thing, or what we call it as that particular impeller, that particular chamber is not filled with water, there is very possibility of air trapped in this particular thing, which will bring the head developed by the air is different from head developed by the fluid. So what will happen? There is a formation of bubbles. So this bubbles will not allow the fluid head develop, or the creation of pressure head will be difficult. So what we try to do actually, the first thing is before starting the pump, before starting the pump, the impeller has to be filled with the working fluid. So what is the working fluid here? It is water. Okay. See, I have to ensure that the impeller has to be merged properly. See, if the impeller is not merged with the fluid, then we will fill the casing through this priming valve. See, we will see. So when we will go for priming actually, so there is something called as a priming valve will be there. This is priming valve. So we'll see that if it is half filled or fully filled. So the process of filling the working fluid to ensure that impeller is properly merged is called as priming. Okay. The process of filling the working fluid into the casing through the priming wall to ensure the impeller is merged. The impeller is merged. Okay, merged in the fluid. Merged in the fluid, that is your water. And this process we call it as priming. So priming is the process of filling the casing with the working fluid to ensure the impeller is properly filled or properly merged. If the impeller is not properly merged, the head developed by the pump is less because of the air trapped in the casing. That's one thing, priming. Now we have another thing. So what we call it as cavitation. So cavitation in centrifugal pump. So cavitation is one more thing which affects most of your centrifugal pump. What is this cavitation? See, if you look at the eye of the impeller, where I am going to see the lowest pressure. Let me go to that sketch. Okay. Suppose if I go to the sketch, look at this. See, this is your eye of the impeller. This is your eye of the impeller. So, in this eye of the impeller, I could see the minimum pressure. At the eye of the impeller, this particular thing, what I am showing here, this particular thing, this is where I could see the lowest possible pressure. So, what will happen? If this pressure falls below your vapor pressure, there is a formation of bubbles. I have to ensure that this minimum pressure never falls below your vapor pressure. If it falls below the vapor pressure, there is a possibility of formation of the bubbles. Once the formation of the bubbles takes place, these bubbles will move with the water, strike the surface. So when they are striking the surface, they collapse and they try to remove the material. And if it is a continuous phenomena, if it is continuously happening, so the material gets eroded. And this phenomena, what is happening? No, This particular thing we call it as a cavitation. Okay, let me write that. Okay, what will happen? So the eye of the impeller, I could see the lowest possible pressure. So I have to ensure that, see, if suppose the pressure at the eye of the impeller falls below your vapor pressure. So under this condition, what will happen? There is formation of bubbles, formation of air bubbles. Okay, formation of air bubbles. And what happens? This bubbles will stick onto the surface. Okay, they stick on to the surface of the. They stick on to the surface of the pipe or casing. Okay. Then what will happen? These bubbles, see, the fluid will be flowing. When the flow of fluid strike these bubbles, they collapse. Okay. The fluid flow, and the fluid flows over these bubbles, they collapse. Okay. Now, this collapsing lead to what is called as this is a continuous phenomenon. This collapsing, if this collapsing of the bubbles, I call it as collapsing of bubbles. If it is a continuous, it happens continuously, then the material gets eroded. It gets eroded, and this leads to what is called as, and all the phenomena what I discussed now, this is called as the cavitation. So cavitation is the process. So it's a method. It's something like it should not happen. So because of the drop in the pressure at the eye of the impeller below your vapor pressure, so there is a formation of air bubbles, and these air bubbles collapse, and they continuously, this collapsing happens actually. Then they try to remove the material from your pipe. So because of this, what will happen? Your friction will increase. So that there won't be any smooth flow of fluid. So lot many disadvantages are there. That's why this cavitation has to be avoided. So to be strictly speaking, the cavitation has to be avoided. How we can avoid it actually? Ensuring that the vapor pressure, the pressure at the eye of the impeller never falls below vapor pressure. And also we have to ensure that maybe MSL, if you look at the MSL, I have to ensure that the pump should not be operated at very high temperatures. Because high temperature means will lead to higher vapor pressure. So lot many interconnectivity is there with your atmospheric conditions. Okay. Now, so the process of filling up this impeller and casing a suction pipe before starting the pump. So that's one thing is called as a piping. And the second thing what we see is actually the cavitation. So the cavitation is collapsing of the bubbles. So these two things we have to look into that. Okay, one is priming, other is the cavitation. Maybe the last topic what we have to look at is your multi-staging of centrifugal pumps. Multi-staging of centrifugal pumps. Okay, when you speak of multi-staging, we have two things in our mind. One is pumps connected in series, pumps connected in parallel. Okay, pumps connected in series, pumps connected in parallel. Let's look at the first one. Pump in series. What is it actually? Now, I do have two pumps like this. I do have two pumps. So, one, okay, two pumps are there. Okay, then I have a sump here. So this is my sump. This is the pump 1 and it is connected to your first sump actually, and output from the pump 1 is the input to the pump 2. Okay, this is your Q out. Okay, this is your Q in, and output from this particular pump. Okay, this is Q1 out, Q2 in, Q2 out. Okay, from the pump is connected to your overhead tank. Okay, I can connect it to the overhead tank. This is my tank. See, what is it actually? What I'm trying to get actually here? See, I am trying to see if you closely observe here. See, this is the head under which your pump 1 is working. Fine. This is the head under which your pump 1 is working. Now pump 2 is working under this head. Now your Q1 and Q2 are same. Okay, Q1 and Q2 are same. That means what is it actually? If you see, if you try to put under H versus Q curve, let me draw that also. Let me draw that curve also, H versus Q curve. So what will happen? This is your head. This is your Q. So if I try to do it actually, what will happen? Your pump 1 will go like this, and your pump 2 will develop like this. This is from pump 1 and this is from pump 2. What has happened here? If I want to deliver the pump 2, this is your H2, this is your H1. So I can conclude something like this. So if I want to increase the pressure head, or I want to get a higher head, so increase the pressure head, the same discharge. Look at this. What the same discharge means? If you try to draw the curve, a vertical line here, so the Q remains the same. If I try to get a higher pressure head for the same discharge, I go for pumps in series. I'll go for a pumps in series. I just have showed 2 pumps. It can be more than 2 also. It can be 1, 2, 3, 4, 5. Higher the number of pumps in series, higher the pressure at what I'm going to get. This is the first one. Now the second one. Pumps in parallel. Pumps in parallel. What I have here actually, I may be having a common, I may be having a sump like this. This is my sump. I'm trying to install 2 pumps actually. They are in parallel. This is my pump 1. This is my pump 2. My pump 2. Okay. This is pump 1. This is pump 2. Now pump 1 is also connected. This will be taking the water. Okay. This is my inlet. So now what I'm going to do actually, this is the outlet from pump 1. So let me call it as Q1. Outlet for pump 2 is Q2. Okay. If I try to connect this pumps discharge out actually like this. So what will be this one? This will be Q1 plus Q2. And this is taken to a tank over a tank like this. Now, if you try to observe it, actually, both the pumps are working under same head. Okay, both the pumps are working under same head. Both the pumps are working under same head. So that's one particular thing which you have to look into it. Okay. This is where this particular thing. This head is head, which is pump. So what we are trying to do, if I try to put the H2 curve for this, actually, the H2 curve will be something like this. This is my H, this is my Q, head versus Q. If I try to plot the curve for this, this is for the pump 1, okay, and this is for the pump 2. So what is it actually? This is for pump 1, this is for pump 2. So what is the head actually? The head almost remains same. This is the head. This is the head actually developed. So now, when I will go for this kind of pump actually, so when I want to increase actually, so increase the discharge. That is, I want more volume of flow at the same pressure head. At the same pressure head. So when I want more discharge under same pressure head, I will go for the pump in parallel. So if I want